now you will appreciate why we had made VGS negative. So, another solution to take care of this parasitic turn on phenomena, one more solution is to make VGS negative. Okay. Right. So, why? If you make VGS negative, that means this voltage, if you try to go into this one, if you try to go into minus 5 volt, then in spite of this happening, okay, in spite of this happening, this point's potential, okay, in spite of this current flowing here and there is a potential increase here, the gate emitter voltage, that voltage will not cause a spurious turn on of the device, okay, due to some unforeseen circumstances. So, because the VGE voltage has been kept to minus 5 volt. Okay. So, therefore, the VGE voltage is generally varying from plus 15 volt to minus 5 or minus 8 volt. Okay. Some another consideration that you should keep in mind is that this RGE. So, often if you keep the IGBT like floating, the gate potential to be floating, then it is not a good idea to keep the gate potential floating, okay, because it can cause unintentional charging of the gate emitter capacitance. Okay. It will build up, this gate emitter capacitance, gate emitter voltage will build up without even the gate pulses. Okay. So, it is always a good idea, in particular for high power applications, that this gate terminal is connected through a resistance RGE, typically about 10 K. Okay. So, that this point is not floating. Okay. Okay. So, this was some of the, these were some of the considerations which we should keep in mind while designing the gate driver board, gate driver resistance and other resistances which we have discussed. Another thing is the power to the gate driver board. Often, like in multi-level converters, gate driver boards are not separately powered from an external source. Okay. They are powered from the DC link itself. Okay. So, there is no separate power supply for the gate driver board. So, if you see the MMC or cascaded edge bridge cells, the cells have this DC link and these DC links are connected to the edge bridge IGBT, for example. When the DC link is available, then we take the power of the gate drive board from that high voltage DC link itself. For example, if it is 1000 volt, we can use a flyback converter to get a 15 volt supply from that 1000 volt DC link and power the gate drive board. This is often done. Okay. So, there is no separate power supply to the gate driver board. It is done because of isolation, because we would like to keep the gate driver board completely isolated. Okay. So, see this, you can see one such gate driver board. Of course, this is not a commercially made, but we have made it in the lab. We just put a picture just to give you an idea that how small this gate driver board actually is. Okay. It is quite small, and here we have used a gate driver IC ACPL337 from Broadcom, and so you can see this is only 3 by 4 centimeter. Even this is not very optimum, you can make the gate driver board even smaller. So, this gate driver board has many protection features as also this driver IC also provides us with that. So, it also has an isolation of the DC-DC converter, and there is also a cut on the PCB, so as to provide a physical isolation. And so, we have been using this gate driver board to drive the SiC MOSFETs, but it can also be used for driving IGBTs or silicon MOSFET. So, now we will talk about bootstrap circuits. Okay. Now, often we see that we will drive, for example, for this kind of voltage source converter, we often drive half bridges, and we have seen that we can use gate driver boards for each IGBTs, upper one high side IGBT one driver, low side IGBT another driver. Now, of course, the question comes up that can we use a single driver for both the devices, and there comes the advantage of a bootstrap circuit. Okay. With a bootstrap circuit, with one single driver or gate driver, we can drive both the upper and lower side IGBTs. For this, we will need some additional components, okay, which we will see here. Okay. But with one source, as you can see here, with one source VDD, we will be driving both the upper and lower side IGBTs. Fine. So, in this bootstrap circuit, what are the components? So, you can see here, this is the power side here, okay, and you have the capacitances, you can also have the capacitances, the gate collector capacitances not shown here, and then you have this voltage source, a single voltage source, and then you have also two transistors here, Q1, Q2, sorry, 4 transistors, Q1, Q2 and Q3, Q4, and some other elements like R gate, D boot, R boot and C boot. Okay. So, the bootstrap basically requires this R boot, D boot and C boot, okay, externally, because nowadays the gate driver ICs, they come along with this bootstrap functionality. Okay. So, this Q1, Q2, Q3, Q4 is also part of the gate driver circuit, it is inside the IC. Okay. So, what you have to give from externally is this R boot, D boot and C boot, these resistance, diode and the capacitance, these 3 elements, and along with that, if you want, if you can have this R gate also, okay, externally you can give. Many ICs are coming up with this Q1, Q2, Q3, Q4 already given to you. Okay. So, let us first see how this circuit operates. Now, suppose in this, let us see this circuit, and I am turning on this transistor, lower transistor, this lower IGBT here, okay, T2, I am turning on T2. In order to turn on T2, I will turn on Q3. So, you have a VDD voltage and the current will flow like this and will complete the path like this, okay, the current will complete the path. So, after turning on Q3, this voltage will give the charge required to turn on this lower IGBT. Now, suppose I want to turn on the upper IGBT. Okay. So, the upper IGBT can be turned on by turning on Q1. Okay. So, I will turn on Q1, and of course, when I am turning on this transistor T1, that IGBT T1, I will turn off T2. How can I turn off T2? I will turn on Q4. So, it can be discharged like this here. So, the lower IGBT operation is pretty simple. So, let me reframe it once more. The lower IGBT operation is pretty simple. With Q3 and Q4 you can charge up and discharge this lower IGBT. But what happens with the upper one? Note that when you are turning on this lower IGBT by turning on Q3, if you have turned on this lower IGBT, then there is a path for current to flow, okay, as shown by this green arrow here. You see, from VDD goes like this through R boot, D boot, C boot and like this here. Okay. There is a path for the current to flow. So, when the T2 has been turned on, this capacitor C boot will be charged to VDD voltage. Okay. Now, this charge, this capacitor C boot which is charged, is now useful for turning on the transistor or the IGBT T1. How? Now, when you want to turn on T1, what will you do? You will turn on Q1 and then this C boot will follow like this here. C boot will discharge and will provide the gate charge required for T1. So, C boot will discharge here. So, whatever charge this C boot had accumulated when the lower transistor was lower T2 was on, now it is discharging here. But note that it should not discharge too much, because if it discharges too much, then this gate emitter voltage of T1 will fall, and we do not want that to fall. We would like to keep the VGA high, so that the on state VCE on is a minimum value, small value. So, we should therefore choose a value of C boot, or the capacitance value should be high, so that it should not discharge much, so that this VGE voltage does not fall. Again, when I want to, so once again when I want to turn on the lower transistor, I will turn on Q3 and I will turn off Q1. Okay, I will turn off Q1, and so this IGBT will discharge through Q2 here, it will discharge through Q2, and this C boot will charge up through the lower path again like this. So, the cycle, so the C boot is again ready for the next cycle. Okay. So, in this way, by using this C boot, we will be able to turn on and off both these IGBTs from a single voltage source. So, this is the advantage. Now, of course, why R boot is needed? Because when the C boot has discharged a lot, then when you are charging this capacitor, if you do not use an R boot, there will be a high inrush current, and R boot will prevent that inrush current. Why will you use a D boot here? What is the function of the D boot or the diode? Note that when T1 is on, okay, when there is this T1 is on, there can be a current flow from this DC bus through T1 through this C boot. Suppose there is no diode here, so the current will flow through this, through here, here and complete the path like that. Okay. Here is the path which I am showing now, VDC through this T1, C boot, R boot, VDD like that, as soon as you turn on the T1. So, therefore, the D boot is necessary and it prevents this short circuit of the DC bus with the control power supply VDD, and it stops that from happening. So, how can you design this bootstrap? It is very easy actually. So, because what will you do? You will see C boot will be charged to. So, when the C boot is getting charged up, it will charge to VDD minus the drop across this one and the drop across T2. Okay. So, this much is the voltage to which C boot will charge up, and the C boot should not discharge much. So, this bootstrap capacitor can be calculated. So, C bootstrap or the C boot, the value C boot is equal to I discharge times delta T divided by delta V bootstrap. Okay. So, because how long it will continue, how long it will discharge? It will discharge for the maximum on pulse width of the high side IGBT, right. So, the duration for which this transistor is on, that is the delta T time, and the total discharge current, average discharge current is I dis. That means, this factor here is the total gate charge required by the IGBT T1. So, this total gate charge of T1 divided by how much voltage we will allow to fall in the bootstrap capacitor, that is what we will. So, this is the total charge divided by the delta VBS, that is the amount of voltage we will allow this to fall. So, that is how you will calculate the bootstrap, and the capacitance you can select 2 to 3 times higher than this value, so as to keep it within a safe limit. Okay. You should also note that the lower side here, lower side IGBT should be turned on for sufficient amount of time, so that this here will be fully charged up. Okay. So, this is for the discharging part, how much delta VBS, but at the same time this device here should be sufficiently turned on, the PWM pulses should be such, this should be fully, so that this capacitor gets the time required to charge it back, to get back its charge from this supply here. In fact, for many such bootstrap circuits, the first pulse should be on this, the first pulse should be on the lower IGBT, because suppose when it is turning on, C boot is fully discharged. So, the first thing before you can really start the converter is to charge this C boot to the VDD value. So, initially you will turn on this device and will charge this C boot to a certain value, then only you can start your operation of the converter. Okay. So, we have taken a very simple example of a bootstrap circuit components for this, this is an IPM, we will talk about this IPM, for this IPM IGBT. Suppose the DC link voltage is 600 volts and the rating of D boot is equal to 600 volts. So, this can be obtained by applying the KVL here. Okay. If you apply the KVL, then you see how much D boot has to block. So, you can see here for example, this is the path where deboot is operating. So, this is the VDC minus this drop plus C boot. Okay. This voltage comes across this terminal, whereas this VDC minus VDD, this comes here on this terminal, okay, on the anode and the cathode. So, how much is it blocking? You can see that it is blocking this full DC bus voltage. So, the voltage rating of deboot must be equal to the or more than the DC bus voltage. So, rating of deboot is equal to the or more than the DC bus voltage, and then R boot you can find out yourself that R boot, because we are doing an RC time constant. So, you can take a 20 to 40 ohm, but you can choose any value, and then you can find out from this how much is the total charge needed, and then can find out that okay, we have given some example here for a switching frequency of 10 kilohertz, that you need a capacitance of 1 microfarad for this particular IGBT which we have used in the lab. So, you can take 1 microfarad capacitance, and the bootstrap capacitor value can be selected a little bit more than this, maybe 2 to 3 microfarad, okay, and this works quite fine. In fact, some of the manufacturers give a recommended bootstrap capacitance in their data sheet. Even they will give a recommended bootstrap capacitance depending on how much is the PWM frequency. So, if this is PWM frequency is low, I mean if the PWM frequency is low, then you will need more bootstrap capacitance. Of course, that is needed because then you will have to hold the voltage for a longer duration of time. So, that is why your capacitance value will increase. We will see little bit of some of the gate driver functionalities which are commercially available in the market. Okay. Gate drivers, there are many gate drivers available in the market and obtained from different manufacturers. For example, ACPL33J, Skyper 32, these are some of the available gate driver circuits. Almost all manufacturers of devices also have their own gate drivers. Now, why I included, we will talk briefly about say next 10 minutes about some of the features of these gate drivers. Why we included this is to understand when you purchase some of these ICs, gate driver ICs, there are certain features which you should be aware of. Okay. So, I included these slides here. You can also make your own gate driver, that is that can be very useful and you have a full control and knowledge over that. However, in many cases the gate driver ICs which are now available, they are number one very compact and they are providing a lot of functionalities, which for a person who wants to make the whole gate driver on his own, he may find it difficult at times to incorporate all these features within a small IC like this much. So, the general trend is to use these commercially available gate driver ICs nowadays. So, there are 4 or 5 important terms. Apart from this, there are other important features also in the gate driver, but isolation, CMTI, under voltage lockout, DSAT detection, these are some of the features of gate driver already available to you. So, what are these features? So, we will briefly explain, because if you purchase some of these gate driver ICs, you will see these terms and some pins associated with it in the IC, and we should be kind of like a little bit knowledgeable about what those pins or what those mean. So, of course, we know that isolation is a very important functionality for a gate driver. Okay. So, because it on one side there is a low voltage and the other side is a high voltage, and so the gate driver basically electrically isolates the low voltage and the high voltage side. It is particularly useful during short circuit in a power circuit. So, optical isolations, magnetic isolations or capacitive isolations are possible. Okay. So, gate driver ICs often give you a voltage rating, that how much is the isolation, how much isolation in terms of voltage, that is given in a gate driver IC. So, based on your application you can choose a isolation voltage with a certain safety factor. Okay. But apart from this, there is one more important rating that you should also look into, is the CMTI rating. Now, what is CMTI? CMTI is a common mode transient immunity, and this is very important in particular for high switching frequency devices like silicon carbide MOSFETs. Now, they are very fast, they can turn on and off very fast. So, what happens with silicon carbide MOSFETs or high switching frequency IGBTs also is that a large voltage transient can occur at between the collector emitter voltage. So, for example, here you can see when this device is turning off, the voltage VCE has a very large dV by dt across this terminal, okay, because it is turning off maybe within hundreds of nanoseconds. Okay. So, and this voltage VDC can be several hundred volts, okay, maybe 1 kilovolt also. So, this voltage during turn on or off can change drastically, okay, in the order of several hundreds of volts per nanoseconds. Okay. Now, although the isolation barrier in the gate drive circuit is present, but they are not ideal. So, that means there is a parasitic capacitance here, and also we know that the gate collector terminals have a capacitance between them. So, what happens is that when there is a high dV dt at this point, when there is a high dV by dt, the circuit gets a path through these parasitic capacitors to flow towards the control side. Okay. So, because of this there will be noise and jitter on the control side, on the gate drive voltage. So, this voltage here, instead of having like a perfect pulse, you will see that there is a pulse, the pulse shape is getting deteriorated and it has jitter in the gate drive voltage, and in the worst case it may happen that there may be a shoot through fault. So, the common mode transient immunity is something which is specified as a quantitative measure for the gate driver circuit against such noise, common mode noise. Okay. So, the driver needs to be able to withstand CMTI above the rated level to prevent noise on the low voltage circuit, and this is given as a value in the gate driver. So, suppose let us take an example, if VDC is 400 volt and the transition time is about 70 nanosecond. So, CMTI is 400 volt divided by 70 nanosecond. So, 5.71 kV per microsecond. So, we must use a gate driver board gate driver IC having a CMTI value which is higher than this 5.71, and this is available in the data sheet of these gate drivers, and you should choose such a value. Okay. It is very important, this CMTI value is very important for silicon carbide or these high switching frequency applications, high switching frequency devices. There is also something which you will see sometimes being used is the UVLO, under voltage lockout. What is that? Under voltage lockout is also a protective feature in the gate driver ICs. So, what happens here is that if VG voltage goes very low, then we know that there are associated problems. The losses will increase and also the conduction loss will increase. So, the UVLO pin in the gate driver IC, there is always an under voltage lockout pin in the gate driver IC that monitors the gate driver gate emitter voltage. Okay. So, it makes sure that this voltage is is above a threshold value. The threshold voltage may be in the order of 13.7 volt for a 15 volt supply. Okay. So, but remember there may be a transient noise sometimes for a false UVLO signal. So, you generally these UVLO pin outputs have passive pull up resistors and filtering capacitors, okay, to get rid of the transient noise and a false UVLO signal. Another thing, this is very important in gate drivers ICs, is the how it protects the short circuit. Okay. Now, often for many unforeseen circumstances, we see that short circuit will happen in the converter. So, during short circuit, a large dissipation of heat will happen inside the device and hot spots will develop and eventually the device will burn. So, the gate driver has the important job of withdrawing the pulse and shutting down the power device in a safe fashion before a catastrophic failure occurs. So, basically how does it do that? Basically it monitors the collector emitter voltage. For example, in an IGBT, if you think of the IGBT protection, the IGBT protection is called as a DSAT, short circuit protection. Okay. What is DSAT? DSAT means desaturation. So, when a high current flows through the IGBT, you can see, suppose this is the IC versus VC characteristics of the IGBT here, and the characteristics typically looks like this, maybe a little bit slope here, slight upward slope here, but more or less the characteristics is looks like this. So, normally the IGBT, for example, is operating normally in the saturation region, because we would like to have the minimum voltage drop across it when it is fully turned on. But now, when a short circuit happens, then a large current starts to flow, and this a large current starts to flow, and this causes the IGBT to move into active region. In active region, the VCE voltage is substantially high and it is of the order of 7 to 10 volts. Okay. So, protection circuits are designed inside the gate driver or with some components outside. They will detect this transition, where they will see that okay, normally when the IGBT is turned on, the normal VCE voltage may be between 1.5 and 2.5 volt, but if there is a short circuit, this VCE voltage suddenly shoots up to 7 to 10 volt. So, by seeing this change in VCE, they will be able to, this gate driver IC will be able to detect a short circuit condition and therefore shut it down the IGBT. Usually IGBTs are shut down within 10 microsecond, maybe 7-8 microseconds only. Okay. Again depends on how is the short circuit withstand capacity of the device. Okay. So, for this we have a circuit. I will not go into the details of this circuit, but basic idea here is that we have. So, this is a driver IC here. There is a additional voltage source inside the driver IC. The driver IC has a voltage source inside, which is made using analog circuits, and then it monitors this voltage here across the collector emitter of the IGBT. So, when this voltage collector emitter voltage crosses this VDE SAT, then this op amp is forward biased and then this pin probably will go high. Okay. So, the circuit will detect the short circuit condition in the IGBT. Okay. So, we will also need this diode, because remember that this VCE voltage when the IGBT is off, this is the total DC bus voltage, and the diode has to block the DC bus voltage from coming across the op amp. In addition to that, there is also this capacitor C blanking, and there is also resistance R blanking, because you see here what means, if you do not use these components, what happens is that every time the switch is turning on, this IGBT is turning on, it is going from the VDC voltage to suppose 2 volts, which is the VCE on of the device. So, suppose if the DC voltage is 600, so from 600 it goes to 2 volt, and suppose this VDE SAT, this voltage is about 7 volts for example. So, every time the device will turn on, it will move from 600, will cross through 7 and will move to 2 volts. So, every time it crosses this close to 7 volts, this op amp will be triggered, which we do not want. We want the DSAT protection to only work when the device has been fully turned on and afterwards if there is a short circuit. So, therefore, there must be a delay inserted in the circuit. Why the delay? Because we would like to wait for the IGBT to fully turn on, okay, and then this DSAT protection should get active. Okay. Otherwise, every time the IGBT is turning on, the DSAT protection will be activated, okay, as it moves from 600 volt to 2 volt for example. So, this delay should be ideally at least the delay for which the IGBT is turning on, that is the total time delay of stage 1 to 4, that much delay must be present, if not more. So, that delay is provided by this RC circuit here along with a charging current here. Okay. So, that part we will not go into the details of this circuit, it is not necessary, but this C blanking will provide you the delay for which the once the IGBT has settled down to 2 volt, after that delay the short circuit protection gets activated. So, that when the IGBT is fully conducting, then a short circuit happens, then the voltage will rise from 2 volt to 7-8 volts, then the DSAT protection gets triggered and it will shut down this IGBT in a safe fashion. Apart from this, we should also understand that short circuit protection for MOSFETs is slightly different than that of IGBT, okay, because of the characteristics. Okay. In case of a IGBT, during short circuit you can see the characteristics looks like this, but in case of a MOSFET the ID versus VDS characteristics is like this, and this means that when a short circuit happens, the current continues to increase in the MOSFET and causing this device to break down at a faster rate. Okay. So, the desaturation voltage of IGBT, although it is 7 to 10 volt, but in case of a MOSFET there is nothing called as a clearly defined region that okay, you monitor VDS and you will get the correct short circuit condition. So, for MOSFET this strategy does not work, the strategy of monitoring the VDS voltage. Instead, in case of MOSFET we use shunt resistor methods. Okay. The shunt resistor values, the voltage across the shunt resistor is monitored and then it will cause this op amp to trigger as the voltage goes beyond a certain limit. So, this is how short circuit or overcurrent protection for MOSFETs work. Okay. So, with this we conclude the our discussion on the gate driver circuits.